So, hello friends, hope you are doing well this period. So, in today's session, I want to focus on another concept of a wind energy conversion system on the practical basis. Today, I just want to cover the concept of wind energy system and particularly its power curve by considering some design examples. So if we can start with the design examples, in that case we need to go for various quantities of the wind turbine like input power, shaft power, rating of the generator, tip speed ratio, power coefficient, wind speed, swept area, air density and some other critical parameters. So first I'll try to cover the fundamental aspect in very short manner and then I shall focus on one of the design example of wind energy conversion system. So if we can start with the basics of wind energy, there are some critical terms. Say for example, one limit is known as the Batty's limit. You will find derivation in number of books of the Batty's limit, even in some lectures also. So it says that no wind turbine could convert more than 59.2% of the kinetic energy into the mechanical energy turning to a rotor. It means that if you have 100% energy in the wind passage and we are considering lossless blades, so in that case the losses are around 40.8%. In this consideration, we are assuming that the turbine is lossless. The lossless system is not existing in the world, so again there is reduction in this percentage efficiency. It is also known as the power coefficient of the turbine at a glance at the initial level. So if you can consider the power available from the wind, it is known as the mechanical power, that is half rho a p cube. If we multiply this power coefficient with this p mechanical, we will get the net power at the shaft. Over here Cp is a function of lambda and beta, where lambda is known as the tip speed ratio over here and beta is known as the blade pitch angle. So you need to go for pitching of the turbine after a certain extent, and this is the equation of the torque of the wind turbine. Now we shall discuss about some terms related with the wind energy systems. So the first is the cut-in speed. So it is a speed at which the wind turbine starts to operate, or it will start deliver the electrical power to the generator. This speed, lesser than this speed, is also known as startup speed. So in startup speed, the wind turbine will operate, it will start to rotate, but the generator will not generate specific amount of power that is to be handsomely penetrating into the grid. The second is the cutout speed. It is the speed where the wind turbine stops the production of the electrical energy and hence the mechanical rotation and turns out from the main wind direction. Usually in a high windy area this thing is common, but the probability of this is very less. The next definition is the tip speed ratio. It is abbreviated as TSR. So it is the ratio ultimately is the speed of the blade at its tip of the blade divided by the wind speed or speed of the wind. The second case is the speed of the wind. As it is variable in nature, the TSR is not constant. So if you can observe there is change in wind speed, the TSR is going to be changed. The next concept is the design wind speed. It is the speed at which windmill or wind turbine reaches as its maximum efficiency. And the next definition is the rated wind speed. Obviously, the name itself indicates that it is the speed at which the machine reaches up to its maximum power, and that speed is known as the rated wind speed. Suppose a machine comprising of 100 kilowatt of power rating, then at what speed, at what wind speed the machine reaches at its rated capacity and it will start generating 100 kilowatt of power, that wind speed is the rated wind speed of the machine. Now this is very broad term. You can access this link in the upcoming slide, that how you can explain this thing practically. So by definition, the tip speed ratio is the speed of the blade at its tip divided by the wind speed. So let's have an example. If the tip of the blade is traveling at 100 miles per hour and the wind speed is 20 miles per hour, if you can considering this kilometer per hour, it is around 32 km per hour and 9 meter per second, then the TSR is simply 100 divided by 20, that is 5. So simply you can put that the tip speed of the blade is traveling 5 times faster than the speed of the wind. Now there is one more importance of this tip speed ratio. So if you can consider that whenever we are considering the tip speed ratio option, at that time we are having various examples of TSI. It means that if your blade, this is the turbine blade, it has a different shape. This shape is also known as the aerodynamic shape of the windmill. So in this case, if you can consider this point moves fast, then compared to this point moves faster, and this point tip moves more faster. But as all the 3 points, these are the arbitrary points, are of the same blade, then blade has to be connected with the hub, and it is so. Then it is to be connected more faster and fastest. But from the unique point of view, it will rotate handsomely faster if the wind speed will be changed. Now let's correlate this term with the importance of TSR. So if the rotor of the wind speed, particularly considering the wind speed, it is too low, then most of the wind will pass through the gap. But if the rotor spin too fast, then the blade will blur and act like a solid wall. So in ultimate case, it has to rotate in such a way that then it has to have enough amount of drag and drift forces that is to be incorporated on the wind turbine, and you will get various value of tip speed ratio by changing in the wind speed. So if we are considering this particularly a video, then you will get various aspects of TSR in this video. So let's run it.
As we've seen in previous pictures, the TSR depends on number of blades in the wind turbine rotor. The fewer the number of blades, the faster the wind turbine rotor needs to turn to extract maximum power from the wind. Just few examples. Two-bladed rotor, TSR around 6. 3-bladed around 5. 4-bladed around 3. Now, if we will design efficiently rotor blade, we can increase these optimum values by as much as 25–30%. And a well-designed typical 3-blade rotor would have a tip speed ratio of around 6 to 7. 6 to 7, perhaps going all the way up to 8, is the best range of TSR that a turbine would like to have. Let's look at this graph. If the TSR is too low, for example, it was designed poorly, and the wind turbine will turn too slow or even stall, we will be on the left of the graph below the cut-in speed. If the TSR is too high, the turbine will spin very quickly, and the wind will see a wall. If the wind see a wall, as we've spoken before, the efficiency go down because the air does not flow through. It like see a wall. So the efficiency goes down, and we are on the right-hand side of the graph. A problem with this too high of rotation of the blade is mechanical stresses. Risk of structural failure. We will discuss about it in depth later in this session. But too high of a rotation means mechanical failures.
So in this session, in this short clip, we've incorporated the one basic understanding of TSR. In this short video, that guy have been mentioned that we have two types of wind turbine. The first is horizontal axis wind turbine, and the second is vertical axis wind turbine. The max limit of horizontal axis wind turbine is 59.2%, and that for the vertical axis it is divided by 2. That is ultimately around 28 to 29% only. So in this consideration, this video is important to try to develop the basic understanding of tip speed ratio. So if you can redefine the same thing in the mathematical form, it is the ratio of 2 pi Rn divided by V infinite, where V infinite is the wind speed without the rotor interruption in meter per second, N is the rotational speed, and A is the swept area, and lambda is the tip speed ratio. It is the non-dimensional. The tip speed ratio of Savonius rotor, it is the vertical axis wind turbine, and multi-bladed rotor, which is used for the pumping purposes, are generally very low. In Savonius rotor, it is vertical axis rotor, and the multi-bladed rotor, as the blades will be increasing, the tip speed ratio will go down. For high-speed horizontal axis grid-tied rotors that we are going to design it today, and the Darius rotor. This Darius rotor is ultimately a spatial rotor. It is the horizontal axis principle based vertical axis rotor. In other words, I can say that it is a vertical axis wind turbine, but it offers all the principles of the lift force, which is the common principle of horizontal axis wind turbine. So in this case, the outer tip actually turns faster than the wind speed owing to the aerodynamic shape. Consequently, the TSR is as high as 9. It can be said that higher the solidity of the rotor, in general, low tip speed ratio would be observed, and it could be applicable vice versa. So our next concept is already incorporated in the initial part of this session, that is the power coefficient. The power coefficient of the wind energy converter or wind energy system is given by the ratio of power output from the turbine divided by the power contained in the wind. The coefficient of the power differs from the efficiency of the wind machine in the sense that the latter includes the losses in the mechanical transmission, electrical generation, converter losses, etc. So the ideal value of Cp is 0.59 for the horizontal axis rotor, and TSR is also an important yardstick for the characterization of the wind energy conversion. So let's discuss about the curves of the power output versus wind speed and the wind speed versus power coefficient. So this is an example I have taken from the one of the renowned company known as Enercon, the datasheet available online free of cost. So you need to find the value of the power at different wind speed and plot the curve of wind speed versus power and wind speed versus CP. The rotor swept area is given 2198 meter square and the rho is 1.225. Now before starting the same thing, how we can calculate? We shall go with this equation of P net. We have half rho A CP. CP is given and the V cube. So we'll use the same equation over here. In the case of this equation, you can find out the value of this power. Inherently, it is given in the sheet. This arrow says that this 4 is cut-in wind speed, 3 is the startup wind speed, 25 is the cutout wind speed. Now, we are going to share this thing and we are going to conclude some most important parameters from this data. But first we can plot the curve. So if you can plot the curve of wind speed that is common on the x-axis, and there are two y-axis. First y-axis is of power and the second y-axis is of the power coefficient. So if you can plot the curve of wind speed versus power, then this is the curve. Now in this curve, after some point of time, the power remains constant. Otherwise, if you would increase the wind speed as per the equation, power is proportional to V cube. It will be very tremendously high, and in the latter case, if the wind speed is so high, then the generator will burn out. So the thing is that we need to restrict the same thing. To restrict the same, if you can plot the curve of the wind speed versus CP, then CP goes down. Now, if you can consider this thing with some digits, we are having 810 after 12 to 13 meter per second wind speed. Afterwards, the power remains same, and there is changing in CP, means CP goes down. Now the thing is that after reaching the rated wind speed of the turbine, the CP is going to be decreased by keeping the power output constant. So we are going to sacrificing the aerodynamic efficiency and the CP is going to be decreased. Now at the cutout wind speed, that is in this case 25, the CP is very low, almost zero. Afterwards there will be a physical rotation of the top of the tower and the wind turbine should be stopped mechanically. It is also known as the yaw control. So after reaching the rated wind speed, the blade pitch angle, that is beta, is going to be activated, known as blade pitch control. There are blade pitch motors. It would be sensed, wind speed would be sensed by the anemometer, and it has been communicated with the pitch motor, and pitch motors are activated after rated wind speed. Now if you can talk about the CP, these are the almost constant CP region. See how it is deviated from the 0.59. So these are the other losses that could be encountered by the wind turbine. And if you can plot the curve of the CP versus wind speed or wind speed versus CP, it observes the curve which is closely related to the second order system. So if you can have a very simple transfer function in S domain, it is 1 upon S square plus S plus 1, and depending upon the wind turbine dynamics, this transfer function will change. So now we have talked about some little bit about the wind turbine power generation curve.
Hello, my name is Phil Ranger. In this video I want to demonstrate the relationship between the rotational speed of the blades of a wind turbine and the power you can extract from it. Mechanical power is needed to generate electrical power. Physics teaches us that mechanical power is calculated by multiplying the torque by the speed. When there is some wind but not enough to make the blades turn, torque is applied on the generator's shaft. But even if there is torque, If the speed is 0, the generator doesn't receive any mechanical power. Now if I let the blades rotate freely, they won't go to an infinite speed. At a certain point, the friction will bring the available torque back to 0. The power available to the generator at this point is also 0 since I have speed but no torque. Power is only available when there is both torque and speed, and the available power follows a bell-like curve. The maximum power for this wind speed would be at this blade's speed. If the blades go faster, there will be less torque, and torque times speed equals less power. If the blades go more slowly, there is more torque but less speed, so there is less power in this case as well. This point is called the maximum power point. It is the optimal blade speed that I would like to have for that particular wind speed. When the speed of the wind changes, the zero torque point changes, as does the entire power curve. More wind means more power at a higher blade speed. Each line on this graph represents the power available at a given wind speed. The maximum power points follow a path that is proportional to the cubic of the wind speed. The goal of a good wind generator controller is to change the current output of the generator to reach the speed that provides the maximum power for each wind speed. This can of course only be done if you have a variable speed generator. Thank you very much.
So, in this discussion, the instructor have produced number of curves. So, if you can have the basic model of wind turbine, that is 1 upon s square plus s plus 1, and you will apply a various wind speed as input, and then you will get the number of curves that has been shown with the change in wind speed. However, this curve is for the various wind speed. At that wind speed, what is the value of power? Similarly, for the sake of simplicity, one more example is there for the self-exercise. That is 900 kilowatt wind turbine. It has the swept area of 1521 meter square, and the rotor diameter is 44 meter. Over here, if you can stop this video over here and you can calculate the power at various wind speed, you will get these results. And accordingly, you can plot the curve. I'm sorry, at the 12 meter per second, it is not shown in the video. It is 710 kilowatt, and the CP is 0.44. And from the 13, it has been seen clearly. This rho is the density of the air. That is 1.225 kg per meter cube. And this is what the power curve of 900 kilowatt wind turbine. See, in this case, after roughly 15 meter per second, rather than that, around 15.5 or 16, the blade pitching angle will be initiated, maintaining the electrical power output constant by decrement in the value or decreasing the value of the CP. Where CP is what? Power coefficient. It is the ratio of particularly power that is to be delivered divided by power containing in the wind. So it is a function of lambda and beta. As the beta is changing afterwards, up to this point of time, beta is almost 0 or it has been pitched with certain degree. Over here I just want to sum up with one example of the fan. If you are using a ceiling fan in our home, it has been slightly inclined. That is nothing but the fixed pitch angle. So there are two types of turbine, fixed pitch and the variable pitch. These are the examples of the variable pitch machine. So you are going to apply some pitching angle, and accordingly your CP is going to be changed, but up to the rated wind speed we are going to extract as much as maximum power is possible. We are keeping beta 0. So up to this point your CP is a function of lambda and beta, but in this case beta is 0. So Cp varies with the change in wind speed because lambda is going to be vary, and afterwards it is a function of lambda and beta. So with this, I'm going to conclude this session. Thank you very much for your kind patience hearing, and hope you will get some fundamental aspect of wind turbine design in context of power output and wind speed, the relationship of the wind speed and the power output, because it is half rho a Cp Vq. So with the change in wind speed, the power is going to be changed because P proportional to Vq, the torque equations and the Cp, and the curves of power output versus wind speed and the Cp versus wind speed. I am again thankful to all. Thank you very much. Have a nice time.